There is a planet in our solar system so enormous, so violent, and so fundamentally alien that even after decades of observation, it still manages to surprise us. A world wrapped in 1,000-kilometre-per-hour winds, crowned by cyclones that have been spinning for centuries, and orbited by moons with active volcanoes, hidden oceans, and geological features we don't yet have names for. Jupiter is not just the largest planet in our solar system. It is, in many ways, the most consequential one, a gravitational colossus that shaped the architecture of everything around it, including the small rocky world we call home. And right now, a spacecraft the size of a basketball court is circling it, sending back data and images that are rewriting our understanding of this gas giant in real time. I'm going to take you through some of the most significant and stunning discoveries that NASA's Juno mission has delivered in its recent orbits. From the hellish, lava-drenched surface of Io, to the deep atmospheric structure of Jupiter's polar storms, to the lingering mystery of how the largest planet in our solar system actually formed. By the end of this, I think you'll agree that Jupiter is even stranger and more spectacular than most people realize. Let's get into it. First, a brief recap for those who haven't been following the mission. Juno launched from Florida in 2011 and arrived at Jupiter after a nearly 3 billion kilometer journey in 2016. Its original mission consisted of 35 polar orbits around the gas giant, which was completed in 2021. NASA then extended the mission significantly, adding dozens of additional orbital passes, called perijoves, which mark the closest point of the spacecraft's path to Jupiter, pushing the total number of planned orbits to 77, with the mission's final act scheduled for late 2025. Each new perijove brings Juno closer to Jupiter's North Pole, providing increasingly detailed data and imagery from angles no spacecraft has captured before. What Juno has revealed over the past several years has fundamentally changed how planetary scientists think about this system. Let's begin with Io. If you've ever wanted to see what Earth might have looked like during its most geologically violent early period, Io is probably your closest approximation. This moon, roughly the same size as our own, is the most volcanically active body anywhere in the solar system. It doesn't have impact craters pockmarking its face the way other rocky bodies do, because its surface is so constantly reshaped by molten lava that craters are simply buried, filled in, and erased before they can accumulate. Io is essentially regenerating itself in slow motion. What drives all of this activity? The answer lies in the geometry of the Jovian system itself. Io orbits extremely close to Jupiter, and as it does, it finds itself caught in a gravitational tug-of-war. On one side is Jupiter, a planet so massive it contains more than 2.5 times the mass of every other planet in the solar system combined. On the other side are Europa and Ganymede, two large moons that orbit farther out and exert their own gravitational influence on Io. This constant pulling and stretching in different directions and at varying intensities generates enormous amounts of frictional heat deep inside Io's interior. That heat has to go somewhere, and it escapes through hundreds of volcanoes spread across the moon's surface. Io doesn't simmer, it screams. Juno's recent close flybys of Io gave us an unprecedented look at this world. In late 2023 and early 2024, the spacecraft swept within approximately 1,500 kilometers of Io's surface, close enough to resolve details that were previously impossible to image from Earth or from more distant spacecraft. What the cameras captured was extraordinary. Lava fountains reaching dozens of kilometers into the sky, glassy plains of cooled rock that reflect sunlight like obsidian, enormous volcanic depressions called calderas, some of them wide enough to swallow a mid-sized country, and plumes, ghostly columns of sulfur and gas rising silently above the horizon, visible in images that looked almost too dramatic to be real. One image from October 2023 caught a plume rising above the Prometheus volcano, one of Io's most persistently active features. Prometheus has been observed erupting by nearly every spacecraft that has passed through the Jovian system: Voyager, Galileo, Hubble. And now Juno has added its own record of this ancient geological fire breather to that list. Another image, captured in February 2024 from just 3,800 kilometers above the surface, showed what appeared to be two simultaneous plumes rising from the same general region. Whether these were two separate volcanoes erupting at once or a single enormous volcano producing two separate ejection columns remains an open question. Juno's microwave radiometer instrument, a piece of hardware originally designed to probe Jupiter's atmosphere, turned out to be remarkably useful for mapping Io's subsurface heat. Because it can detect thermal emissions at depth, scientists were able to identify heat signatures that aren't visible at the surface, helping to construct detailed maps of where Io's interior is most active. These maps revealed something important. Volcanic activity is not confined to the Moon's equatorial and mid-latitude regions. There are volcanoes at the poles too. This distribution has direct implications for one of the biggest outstanding questions about Io, whether it has a global magma ocean lurking beneath its crust. The presence of high-latitude heat sources fits more naturally with models that include a subsurface layer of molten rock encircling the entire Moon, though this has not yet been confirmed. Perhaps the most striking image from these Io flybys came from the infrared mapper, which allowed scientists to overlay thermal data directly onto visible light photographs. The result is a composite view of Io that shows not just what the surface looks like, but where the heat is concentrated. Bright patches of orange, yellow, and white glowing against the darker terrain, each one representing a region of intense volcanic output spanning tens or even hundreds of square kilometers. Some of these hotspots are larger than entire mountain ranges on Earth. And speaking of mountains, Juno gave us a proper look at one of Io's most distinctive landmarks. Steeple Mountain is a towering spire of rock that juts sharply upward from the surrounding terrain, rising somewhere between 5 and 7 kilometers into Io's thin atmosphere. Unlike anything else on the Moon's surface, it has an almost architectural quality to it. Narrow, pointed, almost deliberate in shape. Scientists are still working out how exactly it formed in an environment that tends to flatten and bury surface features under layers of lava. That it exists at all is a small geological mystery in itself. Now let's turn to Jupiter. Everything about Jupiter is a matter of scale. It is nearly 11 times wider than Earth. It rotates faster than any other planet in the solar system, completing a full day in just under 10 hours. Its magnetic field is the most powerful of any planet, stretching so far into space that it would be visible to the naked eye from Earth if it somehow became luminous. And its storms, some of them persistent for centuries, are continent-sized weather systems driven by dynamics that don't have direct analogues anywhere else in the solar system. Juno's extended mission has been steadily moving its orbit closer and closer to Jupiter's North Pole with each successive pass. This progressive trajectory has given the mission's science team something genuinely new, a detailed, evolving record of the polar region's atmospheric structure, captured from multiple angles and at multiple wavelengths simultaneously. What they've found has complicated, in the best possible way, our picture of how Jupiter's atmosphere actually works. At the North Pole, Jupiter hosts a cluster of enormous cyclonic storms, arranged in a roughly geometric pattern. At the center sits one dominant storm, with additional cyclones surrounding it in a ring. These structures have a certain visual symmetry to them. When observed in visible or infrared light, they appear as distinct, well-defined swirling systems of comparable scale. But when Juno's microwave radiometer peers below the cloud tops, that apparent similarity begins to break down. Different storms, which look nearly identical at the surface level, turn out to have dramatically different vertical structures extending downward into Jupiter's atmosphere. Some cyclones that appear modest in visible light show intense microwave signatures, indicating they extend at least 100 kilometers below the cloud tops and have deep roots that influence the atmosphere far below anything we can see directly. Others that are prominent and well-defined in visible and infrared images effectively vanish in the microwave data, suggesting their structure is largely confined to the upper atmosphere and doesn't penetrate deeply at all. The central polar cyclone, the most visually dominant of the group, shows almost nothing in microwave light, hinting that it may be a fundamentally different kind of structure from the storms that orbit it. This variation tells scientists something profound. Jupiter's polar storms are not simply scaled-up versions of each other. They have distinct internal architectures, different vertical extents, and probably different formation mechanisms. Building a proper three-dimensional map of these storms, which is exactly what the MWR team hopes to accomplish over Juno's remaining orbits, could transform our understanding of how giant planet atmospheres organize themselves at depth. Away from the poles, Juno has continued documenting some of Jupiter's most visually spectacular atmospheric features. The folded filamentary region in the planet's northern hemisphere is one of the most photogenic areas the spacecraft has imaged. This is a zone where the powerful east-west jet streams that normally maintain Jupiter's famous banded structure break down entirely. Without the organizing influence of those jets, the cloud material fragments into a chaotic tangle of interlocking vortices, swirling eddies, and turbulent filaments that shift and rearrange themselves over the course of just a few days. In the images returned from orbits 61 through 66, the region looks almost alive, a churning canvas of blue-grey, cream, and brown, constantly repainting itself in patterns that are never quite the same twice. For scientists, these images aren't just beautiful, they're data. The precise shapes and movements of those cloud structures encode information about Jupiter's wind patterns, its internal heat distribution, and the ways in which energy moves through the atmosphere. Understanding how and why jet streams break down in certain latitudes is one of the fundamental puzzles of planetary meteorology, and Jupiter is the best natural laboratory we have for studying it at scale. One of the most unexpected observations from a recent perijove was a photograph taken during orbit 59 that managed to capture Jupiter's tiny inner moon, Amalthea, hanging in front of the planet's stormy face. Amalthea is a small, irregularly shaped moon, only about 84 kilometers across, and it orbits so close to Jupiter that it completes an entire orbit in less than half an Earth day. It's too small to pull itself into a sphere, so it has the irregular, lumpy silhouette of an asteroid. What makes it remarkable, beyond its appearance in this photograph, is its color. Amalthea is the reddest object in the solar system, and it radiates more heat than it receives from the sun at that distance. Why? The leading hypothesis involves electromagnetic induction. As Amalthea moves through Jupiter's powerful magnetic field, electrical currents may be generated within the moon itself, warming it from the inside. Or it may simply be experiencing a modest version of the same tidal heating that drives Io's volcanism. Either way, it is a quietly strange object with a lot left to explain. Perhaps the deepest question Juno is helping to address is also the most fundamental one. How did Jupiter form? This might seem like a question with an obvious answer. Jupiter is a gas giant. It formed from the cloud of gas and dust that surrounded the young sun, end of story. But the details matter enormously, and the details are not agreed upon. One key question is where Jupiter's heavier elements, everything beyond hydrogen and helium, came from. One of the leading theories is that Jupiter's core grew by accumulating water ice-rich material during the early solar system, when icy planetesimals were abundant in the outer disk. If this is correct, we'd expect Jupiter's atmosphere to be enriched in water compared to the Sun. Recent data from Juno's microwave radiometer has allowed scientists to measure water abundance in Jupiter's equatorial atmosphere with more precision than ever before. The results show a water concentration at the equator roughly 3 to 4 times higher than the solar abundance of hydrogen, a strong signal that water is indeed enriched in Jupiter's outer layers. This is consistent with the idea that water ice was a significant source of the planet's heavier elements during its formation. But here's where it gets complicated. Measurements from deeper in Jupiter's atmosphere suggest that water abundance is much lower toward the planet's interior than models had predicted. If water ice was such a dominant player in Jupiter's formation, we'd expect more of it to have settled inward over billions of years. The fact that it apparently hasn't, or that what's there is lower than expected, is creating real friction between the observations and the models. It means either our understanding of how Jupiter formed is incomplete, or the way water behaves inside giant planet interiors is different from what we've assumed. Possibly both. This is the particular joy and frustration of planetary science. Every answer arrives carrying 2 or 3 new questions tucked inside it. Juno was built to probe Jupiter's water abundance, and it has done exactly that, and in doing so, has made the mystery of Jupiter's origin more intricate, not less. By the time Juno was expected to end its extended mission in 2025, it had already completed more than a decade of exploration. But the spacecraft did not simply fade into history. Even in 2026, NASA was still using Juno's data and preparing new flybys of Jupiter, showing that the mission had continued beyond its original expected timeline. And when Juno finally reaches the true end of its journey, NASA's plan is not to leave it drifting around Jupiter. The spacecraft is expected to dive into Jupiter's atmosphere, where pressure, heat, and friction will destroy it completely. This protects moons like Europa and Ganymede from even the smallest risk of contamination. A mission launched to study Jupiter's origin and interior ended up revealing something much bigger, a violent, complex world surrounded by moons that may hold clues about life beyond Earth. Jupiter does not give up its secrets easily, but Juno has been remarkably persistent. And if you want to keep exploring the hidden worlds of our solar system, subscribe to the channel and watch the next video on your screen now.